Hi everyone, so today we are going to look at the tutorial 8. So for this tutorial I'm going to just write down the equation and explain the different steps on a piece of paper, as I do not have access anymore to the campus and to a whiteboard. So I hope this is going to be easy to understand for you. But in case you have some question, do not hesitate to contact me by messages on QRQs or by email. All right. So before I go into more detail regarding the problems, I wanted to address something that I said last week. So regarding the which model would be more relevant to which type of test. So in the problem 1, actually, we are going to answer partially this question. We are going to look at a specific model, and you are going to try to be able to see how it behaves depending on two configurations. So the creep configuration and the stress relaxation configuration. So from this, you are going to be able to appreciate why one model will be more suited than the other for different tests. So let us start it with the problem 1. Okay. So in the problem 1, we have a system where we know that the biopolymer has a relaxation modulus, a stress relaxation modulus that can be expressed as, okay, this is the expression for the stress relaxation modulus over time. So we know that G0 equal to 2 gigapascal, and we know that at T equal 10 power 4 seconds, it is equal to 1 gigapascal. Okay? So that means that we can rewrite this stress relaxation modulus expression as followed. Okay? So it means that you can just easily solve this, right? And then you would end up with something that looks like this. Okay. So from this, we are going to be able to calculate the relaxation time very easily, right? So the relaxation time will be equal to 14,426.9 seconds. Okay. So now let's continue with this. So if we know the relaxation time for this biopolymer, we are able to calculate its viscosity. So the viscosity would be expressed as, all right, or you can just rewrite this as followed, right? At the time equals 0, huh? And we will obtain a viscosity of 2.88 times 10 power 4 gigapascal per second. So this is just we are just calculating this as all those information are provided in the problem, and it seems like we may need this later on, so why not calculate it right away? So the question reads itself as to derive. So we want to derive for this biopolymer, we want to derive its creep compliance and evaluate the strain 1000 seconds after the rapid application of a stress of 100 MPa. So if we were to look at this system, so here we are working in a stress relaxation. All right, so stress relaxation. Now we are going to work in creep. So since we work in a creep, it means that we have constant stress, sigma 0, of, in this case, of 100 megapascal. And we want to know the strain epsilon equal epsilon 1000 second. So we need to be able to derive a relationship for the stress and strain to be able to get there. So how to do? So here we have to remember a bit what we know from those models. And when you look at the relationship for the stress relaxation, this relationship here, you notice that it looks very familiar. And you should be able to recognize that this expression is typically what you obtain for the stress relaxation of Maxwell model. So if you imagine this expression now, and if you were to plug in some values, you would see that at time equals 0, right when we apply the strain, so say it's 0 here, we'll have an instantaneous rise. We'll have G0 equal G0, right? So this term cancels. So from this we obtain like a very sharp rise. And then after we will have the time kick in, and kick in stronger and stronger and stronger until the exponential becomes close to 0. So we will have a decrease, a slow decrease like that, all right? Until reaching 0 here. And we can, yeah. So that would be the time here, and that would be the stress applied on the modulus, sorry. The evolution of the modulus, okay? So we'll have a sharp increase, and then this decrease. So this kind of behavior, you could model it with a spring and a dashpot, right? So you have the spring that gives you an instantaneous response. So this is why you have this like instantaneous increase in the modulus as you apply some strain. And then you will have the dashpot slowly kicking in, and as time passes, as the time increase is going to completely is going to slowly decrease. The modulus is slowly going to decrease until reaching 0. So you should, from this expression that you saw here, you have to be able to recognize that we are working with a system that can be modeled by a Maxwell model. So if you know this, then we can start to work around with the derivation. So let's set up our Maxwell model. So we will have a system with spring 1, dashpot, and we're applying stress sigma 0 and sigma 0. So we have E1 up, viscosity, right? And we'll have epsilon 1, epsilon 2, so which will be the strain on 1 and the strain on 2. So we have to derive a model for this in terms of creep compliance, right? So to do this, so first we have to put forward the assumption that we know for a Maxwell model. So the Maxwell model is that we know that sigma 1 equal to sigma 2 equal to sigma. So the stress on the spring and the stress on the dashpot is equal to the strain, the stress applied on all the components. Okay. On the other hand, strain applied on 1 plus strain applied on 2 equal to the total strain on the model. So you should be familiar now with playing with this kind of assumption. So you see, if this is in series, essentially you have the accumulation of the strain and the equivalency of the stresses. On the other hand, when you have the system in parallel, such as a Kelvin void system, you would have the stress that are cumulative and the strain that would be equal on each component. So knowing this, first let us derive the system with the spring. So for the spring, we know that the stress applied on 1 equal to the modulus E1 or G1, right? Epsilon. So epsilon 1. Okay. So if we derive this, we're going to say all right. That holds true. So you would say after, you could say that did sigma 1. Sorry, you would say the expression as follow. All right. So we have expressed the derivative of the strain over time for the spring. So now we know that for the dashpot, on the other hand, we have a system where we know that the expression is equal to sigma 2 equal to viscosity. This is the expression that we know for a dashpot. So we can rewrite it as all right. So now we have d epsilon 1 over time, d epsilon 2 over time, so the two derivative. So we remember this expression. We can also state this, right? So then, continuing with this, we would just write the following expression. All right, so we would write the following expression. So we are getting quite close here. So now in looking at this expression, we have to remember that we are talking about a creep test, right? So what does it mean, a creep test? It means that we are applying a constant stress. So if we have a constant stress, this means that the derivative of this stress over time is equal to 0. So we can see that we can just cancel this term. So we can just write down that the derivative of the strain over time is equal to the stress on 2 divided by the viscosity. And we know that the stress on 1 is equal to the stress on 2 is equal to the stress applied on the system. So we can just write this as the derivative of the strain over time is equal to the stress divided by the viscosity of the dashpot. So now, solving this is easy enough. This is a very simple expression. So we are just going to write down, we are just going to integrate the system, and we are going to obtain something that would look like that. Okay. Now the challenge is to, now the last thing to do is to obtain the constant, the value of the constant. So what do we know is that we know that at epsilon at time equals 0, we have, or if we plug in the values here, we have the strain at epsilon 0 that is equal to C, right? Because the time cancels. On the other hand, we also know that the dashpot will not kick in at t equals 0, and we would know that the stress applied on this composite will be equal, on the biopolymer will be equal to the modulus times the strain on epsilon 0. So we can make this assumption because we know that t equals 0, the dashpot does not kick in yet. This is just about the spring, right? So that's why we can just write this expression. So from this, we can just say that epsilon 0 is equal to sigma 0 over E. We know that the modulus at t equals 0 is equal to 2, right? 2 gigapascal. So we would write sigma 0 divided by 2. Okay. So now that we know that the constant C is equal to sigma 0 over 2, we can just write the final expression. That would be that the strain over time is equal to stress divided by the viscosity times the time plus sigma 0 over 2. This is our complete expression for this Maxwell model for the evolution of the creep over time. So now the only thing that is left to do is to calculate the strain at 1000 seconds. So epsilon of 1000. So we are going to say epsilon 1000 is equal to sigma 0 by the viscosity times 1000 plus sigma 0 divided by 2. So we are going to be careful with the unit, right? We are going to make sure that we put everything in gigapascal. So that would be equal to the following. Okay, and from this we obtain the value of a strain of 0.05347. All right, so I hope that's clear for everyone. So we just derived, we just make the assumption of from the stress relaxation, from the form of the stress relaxation, we made an assumption related to the type of model that can be used to model this biopolymer. So we identify this, that it looks like a Maxwell model. So we just put forward the Maxwell model and make the assumptions related to having the system experiencing creep, and then we derived accordingly, and we obtain an expression of that relates the stress and the strain. And from that, we just calculated the strain at 1000 seconds when you have a constant stress applied of 100 megapascal, and we obtain this value of strain. So now, the one thing that I want to spend a few seconds to talk about with you is that if you look at this form, you realize that essentially, if you were to use this kind of model to look at a creep test, and you were to plug in so we are going to look at the evolution of the strain over time. All right. So you see that we have the stress divided by the viscosity times the time plus the stress divided by the modulus. So we'll have at t equals 0 we have this instantaneous rise. Okay. So this is the elastic component of the system. But then after, as we are going to have the time kicking in, you will realize that this is just going to look like a straight line. Okay? And it's going to continue indefinitely. So what does that mean? So what it means is that this system is probably not suitable to describe a creep test, right? Because no biopolymer will have the strain elongate, the strain increase over time linearly like that. Typically, for a polymer, you would have a behavior that would look like so the instantaneous rise, all right, and then a logarithmic like increase over time until you reach a plateau. All right. So it means that the Maxwell model, in general, is okay for stress relaxation and not okay for creep. And actually, for the Kelvin-Voigt system, it's the opposite. So it'd be more suited to describe a creep test, but not well suited to describe a stress relaxation test. So it's kind of a quick note on the use of each model for different systems. So this is the end of the problem 1. So I will. So if you have any questions, just don't hesitate to send me an email, contact me so that we can discuss about the problems further. All right, thank you, and I will start the problem 2 shortly.